Oxford philosopher Nick Bostrom calculated the mathematical probability that we're living in base reality versus a computer simulation. His conclusion challenges everything we assume about existence. If advanced civilizations can create realistic simulations, we're statistically more likely to be in one than in the original universe. MIT physicists have discovered mathematical structures in fundamental physics equations that remarkably resemble error-correcting computer code. Meanwhile, researchers at the University of Washington demonstrated that DNA can store and execute digital information, including computer programs that can attack other computers. These discoveries don't prove we're living in a simulation, but they raise profound questions about the nature of reality that deserve serious scientific consideration. Tonight, we'll examine the evidence that has convinced some brilliant minds to take simulation theory seriously, while also exploring why others remain skeptical. I'm Professor Morpheus, and this investigation might change how you think about existence. If you're curious about reality's deepest mysteries, subscribe for more investigations into what might be humanity's greatest questions. Now, let's examine the evidence. The simulation hypothesis didn't emerge from science fiction. It came from rigorous philosophical analysis by Nick Bostrom at Oxford University in 2003. His simulation trilemma presents three possibilities, and the logic forces us toward an uncomfortable conclusion. First possibility: civilizations typically destroy themselves before developing advanced simulation technology. Think about our own trajectory: nuclear weapons, climate change, artificial intelligence risks. Perhaps most species eliminate themselves before achieving cosmic-scale computing power. Second possibility: advanced civilizations develop the capability but choose not to create realistic simulations of their ancestors. Maybe there are ethical constraints we haven't considered. Perhaps simulating conscious beings capable of suffering is considered morally unacceptable by advanced species. Third possibility: we are almost certainly living inside an ancestral simulation right now. This conclusion emerges from pure mathematical reasoning about probability distributions. Bostrom's reasoning is mathematical. If any civilization anywhere develops simulation technology, they likely wouldn't create just one. Consider our own computing trajectory. We don't build single processors, we build millions. We don't create one video game, we create entire libraries of virtual worlds. An advanced civilization with universe-scale computing power might create thousands or millions of simulated histories. They could run every possible variation of their evolutionary development. They might simulate alternate outcomes of major historical events, different technological development paths, various social structures. The statistical implication becomes stark. For every real civilization, countless simulated ones could exist. If there are 1 million simulated worlds for every real one, you have a 1 in a million chance of being in the original. When asked about these odds, entrepreneur Elon Musk famously responded that the chances we're in base reality are billions to 1 against. Astrophysicist Neil deGrasse Tyson more cautiously estimates 50-50 odds. Both acknowledge the logical force of Bostrom's argument, even while recognizing its speculative nature. But here's what makes this more than philosophy. We're rapidly approaching the technological capability to test these ideas experimentally. Our own computing power grows exponentially. Video games already create convincing virtual worlds. Artificial intelligence systems demonstrate increasingly sophisticated behavior. If we can create realistic simulations within the next century, Bostrom's logic suggests we're almost certainly already in one. The creators would be just a few technological steps ahead of where we are now. But let's move beyond philosophy into hard physics, because what we've discovered about the fundamental structure of time itself might be the strongest evidence yet that reality operates like a cosmic computer program. If we live in a simulation, we might expect to find evidence in the fundamental structure of reality. Some physicists point to intriguing limitations that could suggest computational constraints built into the fabric of existence. Consider Planck time, approximately 10 to the minus 43rd seconds. This represents the smallest meaningful unit of time in physics. Below this threshold, our current theories suggest time becomes undefined. The equations of general relativity and quantum mechanics simply break down. Think about what this means. Time, the most fundamental aspect of our experience, has a minimum resolution. Like pixels on a screen or frames in a video, there's a smallest possible slice of temporal reality. Some physicists interpret this as evidence that reality operates in discrete steps, like frames in a cosmic video game. Each tick of Planck time represents the universe updating its state, calculating the next moment of existence. However, physicists debate whether this represents an actual property of time or simply the limits of our mathematical models. The discrete nature of Planck time could reflect the granular structure of space-time, or it might indicate where our current physics breaks down rather than proof of digital reality. But consider the implications if time truly is pixelated. Every computer processes information in discrete steps. Your smartphone updates its display 60 times per second. Video games render new frames at regular intervals. A universe operating in Planck time steps would function identically. Einstein's speed of light limit provides another intriguing parallel. Nothing can exceed roughly 300 million meters per second in a vacuum. In computational terms, this resembles a processing constraint, a maximum rate at which information can propagate through the system. Think about video games again. Every game has processing limitations. Loading screens exist because computers need time to render new areas. Draw distance limits prevent systems from calculating too much simultaneously. Frame rate caps prevent the processor from being overwhelmed. Simulation advocates suggest the speed of light serves the same function, preventing us from accessing regions of space-time that haven't been rendered yet. If we could travel faster than light, we might reach parts of the universe that exist only as simplified placeholder data. Skeptics counter that the speed of light emerges naturally from the mathematical structure of space-time itself, requiring no computational explanation. Einstein's equations predict this limit as an inevitable consequence of how mass, energy, space, and time relate to each other. Yet the parallel remains striking. Both video games and our universe impose strict speed limits to maintain system stability. Both operate with fundamental time units to process information. Both exhibit behavior consistent with computational resource management. There's also the curious question of why our universe has any limits at all. If reality emerged from purely physical processes, why should there be maximum speeds, minimum time units, or quantized energy levels? These constraints suggest an underlying architecture, rules built into the system rather than emergent properties of infinite possibility. But perhaps the most disturbing evidence comes from biology itself. Scientists have successfully stored computer viruses in DNA, and those biological molecules can hack digital systems. The boundary between life and software has been permanently erased. Perhaps the most accessible evidence for simulation theory comes from collective false memories, the Mandela Effect. Millions of people share identical recollections of events that apparently never occurred in our current timeline. People distinctly remember Nelson Mandela dying in prison during the 1980s, complete with memories of his funeral broadcast on television. Many remember watching his wife walking beside the casket, the ceremony lasting 2 hours. They remember the global reaction, the news coverage, the historical significance, but according to official records, none of this happened. Mandela died in 2013. Many recall the Berenstain Bears children's books with an E, though they were always spelled Berenstein with an A. Countless people remember the Monopoly mascot wearing a monocle over his right eye. He never had one. The corporate mascot for Planters Peanuts wears the monocle, but somehow this memory became attached to the wrong character. Darth Vader's famous line presents another example. Most people remember him saying, "Luke, I am your father." The actual line from The Empire Strikes Back is, "No, I am your father." The misremembered version has become more famous than the real dialogue. These aren't isolated incidents involving a few confused individuals. We're talking about millions of people sharing identical false memories with remarkable consistency and emotional conviction. They don't just intellectually believe these things happened, they have vivid, detailed recollections. Simulation theorists interpret these as glitches, moments when the program updates with new information, creating inconsistencies in the historical record. Science fiction writer Philip Dick, who experienced reality shifts personally, proposed that our world occasionally branches into new timelines, and false memories are remnants of previous versions. Dick theorized that what we call déjà vu occurs when the simulation corrects itself with updated information. That eerie feeling of having lived a moment before happens because we have, in a previous iteration of the program, our consciousness briefly remembers the earlier version before the system overwrites our memory banks. Mainstream psychology offers alternative explanations that don't require cosmic programming. False memories can spread through social networks, reinforced by media representations and cultural references. Our brains often confuse similar information, especially when processing childhood memories or pop culture references. Memory researchers have demonstrated how easily false recollections can be implanted and reinforced. Once established, these memories feel completely authentic and resist correction even when presented with contradictory evidence. The Berenstain versus Berenstein confusion might result from common English spelling patterns. Most names ending in Stein use that spelling, so our brains automatically correct the unusual Stain ending. The Monopoly monocle confusion could result from associating wealth imagery with the character. Yet simulation advocates argue that these psychological explanations, while plausible, don't fully account for the extraordinary consistency and emotional intensity of Mandela Effect experiences. Why do millions of people make identical errors rather than random variations? Why do these false memories cluster around specific cultural touchstones rather than distributing randomly? The Mandela Effect might reveal more about human psychology than cosmic programming, or it might represent our first glimpse behind the curtain of programmed reality. The evidence remains ambiguous, but the questions it raises demand serious consideration. But what we found embedded in the equations of physics itself might be the most compelling evidence yet. computer code, actual programming instructions hidden in the fundamental mathematics that govern reality. Nature exhibits mathematical precision that some find suspiciously computational. The Fibonacci sequence, where each number equals the sum of the previous two, appears throughout the natural world with remarkable consistency that suggests algorithmic rather than random processes. Sunflowers display 21, 34, 55, or 89 spirals in their seed arrangements, all consecutive Fibonacci numbers. This isn't approximate or coincidental. The spirals are precisely countable and consistently follow this mathematical sequence across millions of individual plants. Pine cones, pineapples, and cauliflower heads follow the same pattern. Flower petals typically number 3, 5, 8, 13, or 21, never 4, 6, 7, or 12. Nautilus shells grow in spirals that conform exactly to the golden ratio derived from Fibonacci sequences. These patterns extend beyond individual organisms into the structure of galaxies, hurricane formations, and the geometry of human DNA. The double helix measures 34 angstroms long by 21 angstroms wide, both Fibonacci numbers appearing in the molecular blueprint of life itself. Beehive hexagons demonstrate another form of mathematical optimization. The hexagonal structure provides maximum storage capacity with minimum material usage, a solution that would emerge from algorithmic optimization rather than random trial and error. The ratio of female to male bees in any healthy colony consistently equals 1.618, the golden ratio. This proportion appears to be maintained automatically across different species, environments, and seasonal variations. It's as if the colony operates according to programmed parameters. Spider webs follow mathematical algorithms for maximum strength with minimum silk expenditure. The radial and spiral thread placement follows predictable geometric patterns that optimize structural integrity. Even crystals form according to precise geometric rules that mirror computer algorithms for three-dimensional space filling. Simulation advocates see this as evidence of underlying code, mathematical algorithms governing natural processes. MIT cosmologist Max Tegmark observes that if he were a character in a computer game, he would eventually discover that his world operated by rigid mathematical rules reflecting the computer code of his reality. But evolutionary biologists offer natural explanations that don't require cosmic programming. Mathematical patterns often emerge from optimal solutions to survival problems. Fibonacci spirals maximize seed packing efficiency because that arrangement captures the most energy from sunlight. The golden ratio appears in systems that grow through repeated division and expansion. Natural selection favors mathematical optimization. Organisms with efficient resource usage, structural stability, or energy capture survive and reproduce more successfully. Over millions of generations, mathematical precision emerges from competitive pressure rather than deliberate programming. However, this explanation faces a significant challenge. How does random mutation and natural selection consistently arrive at mathematically perfect solutions across vastly different biological systems? Sunflowers, nautilus shells, galaxy formations, and bee colonies have no evolutionary connection, yet they all follow identical mathematical principles. Physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in describing nature. Why should abstract mathematical concepts perfectly describe physical reality unless reality is fundamentally mathematical in nature? unless it represents computation running on cosmic hardware rather than physical processes running on material substrates. The question becomes, do we find mathematics in nature because our brains evolved to recognize patterns that actually exist in a physically real universe, or because the universe is literally made of mathematical relationships, information processing rather than matter and energy? Recent research has blurred the line between biological and digital information in ways that simulation theorists find compelling. Scientists have successfully demonstrated that DNA functions as biological hardware capable of running digital software programs. The research team at the University of Washington, led by computer scientists and geneticists working together, embedded complete digital files into synthetic DNA sequences. We're not talking about simple data storage. They created functional programs that could execute instructions and modify other systems. 1 gram of DNA can theoretically store 215 petabytes of information, equivalent to roughly 200,000 laptops worth of data, compressed into a space smaller than a sugar cube. But storage capacity was only the beginning of what they discovered. More provocatively, the researchers demonstrated that DNA could carry executable malware. They crafted genetic sequences containing malicious code designed to compromise computer systems analyzing the biological material. When DNA sequencing software processed their specially designed sequences, it triggered security vulnerabilities in the analysis programs. This proof-of-concept experiment revealed that the boundary between biological and digital information is far more porous than anyone had imagined. DNA doesn't just store information, it can execute programs, modify systems, and interact with digital networks. Biological matter was literally running software and attacking technological systems. The implications stagger the imagination. If DNA can store executable code, what distinguishes biological life from sophisticated software? Are we organic computers running genetic programs, or are we digital constructs simulating biological processes? Microsoft researchers have expanded this work, storing entire databases in synthetic DNA with perfect retrieval accuracy after months of storage. They encoded high-definition video files, complete software applications, and complex databases into genetic material. The information density exceeds anything possible with silicon-based technology. Harvard geneticist George Church encoded his entire book, Regenesis, into DNA format, 53,000 words transformed into genetic sequences. They created 70 billion copies of the book, each smaller than a speck of dust. The storage density exceeded current silicon technology by a factor of 1,000,000. Church's team also encoded images, audio files, and even primitive animations into DNA. They developed methods for random access retrieval, error correction, and file compression using biological molecules. DNA was functioning as a complete computing platform. But critics note important distinctions that limit the simulation theory implications. These experiments used artificially synthesized DNA designed specifically for information storage, not naturally occurring genetic material. The synthetic sequences were created using advanced laboratory techniques and don't represent how natural biological systems actually operate. Natural biological systems evolved for reproduction, metabolism, and survival, not data processing or program execution. The fact that we can repurpose DNA for digital storage doesn't necessarily mean that naturally occurring genetic material functions as computer code running cosmic software. However, this objection may miss the deeper implication. If biological and digital information systems are fundamentally compatible, if DNA can seamlessly store and execute computer programs, what does this suggest about the underlying nature of both systems? Perhaps the distinction between biological and digital is artificial. Maybe information is information regardless of whether it's stored in carbon-based molecules or silicon-based circuits. Maybe consciousness and computation are different aspects of the same phenomenon, information processing creating the experience of awareness. But quantum mechanics provides perhaps the strangest evidence yet. Experiments prove that the act of observation can retroactively change events that happened millions of years ago across vast cosmic distances. Reality appears to update its own history based on what consciousness chooses to observe. Perhaps the most intriguing evidence comes from theoretical physicist James Gates Jr. at the University of Maryland. While studying the mathematical equations that describe fundamental particles, Gates discovered something that should not exist in a natural universe. Working with supersymmetric field theories and string theory equations, the most advanced mathematical descriptions of reality's basic building blocks, Gates found mathematical structures that closely resemble error-correcting codes used in computer programming and digital telecommunications. Specifically, he found doubly even self-dual, linear binary error-correcting block codes. These are the same mathematical tools that allow your web browser to function correctly, your smartphone to maintain clear calls, and your streaming video to play without corruption. They detect and fix errors in data transmission automatically. Finding these structures in the equations that govern quarks, electrons, and other fundamental particles struck Gates as remarkable. He wasn't looking for computer code, he was trying to understand the mathematical relationships that determine how matter and energy behave at the smallest scales. Initially skeptical of simulation theory, Gates acknowledged that this discovery forced him to reconsider everything he thought he knew about the nature of reality. He stated that he could no longer say people like Max Tegmark are crazy for proposing that reality might be computational rather than physical. But Gates himself emphasizes caution in interpreting this finding. Mathematical structures can appear similar without being identical in function. The resemblance between physics equations and error-correcting codes might reflect deeper mathematical principles rather than evidence of literal computer programming. Some physicists argue that if reality is fundamentally mathematical, as suggested by the unreasonable effectiveness of mathematics in describing natural phenomena, we should expect to find similar mathematical structures across different domains. The appearance of code-like patterns in physics might be mathematically inevitable rather than evidence of artificial construction. However, this explanation raises its own profound questions. If mathematical structures appear inevitably across different domains, what does this suggest about the relationship between mathematics and reality? Is mathematics something we discover in nature, or something that nature is literally made of? John Wheeler, who collaborated with Einstein and worked on the Manhattan Project, proposed that reality emerges from information rather than matter. His "it from bit" hypothesis suggests that every particle, every field, every aspect of physics originates from binary informational processes rather than physical substances. Wheeler suggested that the universe is a self-exciting circuit, a cosmic information processing system that writes itself into existence. The observer and the observed are part of the same computational loop, with measurement extracting information from the universal database rather than detecting pre-existing physical properties. Modern quantum field theory supports this information-based interpretation. Quantum fields don't contain particles as we normally imagine them. They contain probability amplitudes, mathematical relationships that determine the likelihood of finding specific measurement outcomes when consciousness interacts with the field. When we measure a quantum system, we're not detecting physical objects with definite properties. We're extracting specific bits of information from a vast computational matrix that contains all possible outcomes in superposition until observation collapses the wave function into a definite result. If physics equations contain error-correcting codes, this might represent the universe's method of maintaining data integrity across vast scales of space and time. Like any information processing system, cosmic computation would need mechanisms to prevent corruption and maintain consistent results despite quantum uncertainty and relativistic effects. But we may be approaching a critical threshold that could reveal the truth about our reality. Humanity is creating digital information so rapidly that we're approaching what scientists call the information catastrophe, a point where our data creation might exceed the computational capacity of the universe itself. After examining all this evidence, we find ourselves in a position of informed uncertainty. The simulation hypothesis remains scientifically untestable. Any evidence could theoretically be simulated, and any refutation could be programmed into the simulation by its creators. What we've discovered are intriguing parallels between observed reality and what we might expect from computational systems. Pixelated time, mathematical optimization in nature, quantum observer effects, cosmic fine-tuning, and digital biological convergence all raise fascinating questions without providing definitive answers. Perhaps the most important insight is that simulation theory forces us to think carefully about the fundamental nature of reality, consciousness, and existence. Whether we're biological entities in a physical universe or digital constructs in a cosmic computer, we remain thinking beings capable of wonder, discovery, and meaning-making. The relationships we build, the knowledge we gain, the creative works we produce, and the moral choices we make retain their significance regardless of the underlying substrate of reality. Love, curiosity, creativity, and ethical behavior have value whether they emerge from biological processes or computational algorithms. Science fiction writer Philip Dick once wrote that reality is that which, when you stop believing in it, doesn't go away. Whether our reality is computational or physical, it continues to present us with genuine challenges, authentic experiences, and real consequences for our actions. The simulation hypothesis may never be definitively resolved, but in wrestling with this question, we engage in the most fundamentally human activity, using reason and evidence to understand our place in existence, whatever form that existence might take. And perhaps that search for understanding, whether conducted by biological brains or digital minds, represents something genuinely meaningful in any possible universe. The question isn't whether we're real, it's what we do with the consciousness we've been given, simulated or otherwise.